Okay, so now how does this still help us, right? Again, we have to come back to what it is. Okay, the reason it helps us is if you do all that. Okay, and now I'm going to again tell you the end of the story. I'm telling you the conclusion of the story without telling you how the thing is solved. Okay, remember this chronic penny model. Okay, when you have that KP model, right, chronic penny model, we had this series of potential wells, and it, I'll say now, can be solved. Okay, when I say that, it essentially, I mean, it involves a lot of mathematics, so we don't want to do it. So it can be solved, and if you solve it, you will start seeing that you have corresponding to, you saw that in the previous case, corresponding to each level, you had two levels, right? The delta E was there. Now, if you have n levels, what you'll start seeing is you will have n levels which are allowed. Okay. Okay. Again, there's a gap. Again, there will be n levels which are allowed. All right. So if you plot the energy versus K relation for this chronic penny model, you'll start seeing that it sort of behaves in a similar way to the traditional parabolic dispersion. That sort of a shape is there overall. Okay, but in addition to that, what you see is that you have some first band of energies which are allowed. So when they're allowed, you have the blue curve right here. You have this allowed bands and forbidden bands. So in between, there are some solutions which are not allowed. That means you cannot have an electron having that particular energy. Okay, so that is it. It turns out that it comes out to be this. Okay, so because you have n levels, and basically each of this is consisting of very, very, very small levels, and all of them essentially are, the gap is so small that you can consider them to be a band of continuous levels. Okay, the difference delta E is going to be not negligible in the physical case. Okay, all right. So again, there is one more small thing. I just want you to in some sort accept it. Okay, so the solution here has a form, a function which is basically cos k times a. Okay, well, yeah, this is from the textbook. Whenever I show you the figures with this caption here, like in this form, caption is written, right? It is from the textbook. I'm just, it's from Donald Lehman's textbook. You can go back and refer to the particular figure, and then you can read a little bit more. That's why I just want to leave those figure captions in the place. Okay, but I don't provide any references. Whenever I take it directly from the textbook, I'm not providing references. But the caption should tell you that you should go back and look in Neiman. Okay, if you want to understand the details. Okay, so this has in the textbook, in the class I have used, in the lecture I have used L as the width of the well. In the textbook they use L A. Okay, so basically A is the well width. That's why it is coming like this. But essentially it's the same thing as we use L. Okay, so it turns out that they have a dependence of cos k, and we know that this is equal to cos 2n pi cos 2n pi plus ka. That means if I put plus 2 pi and minus 2 pi, if I add and subtract, it's not going to change. Okay. So what happens is this dispersion, it becomes complicated for us to just draw it all the time. So what we do is we take this particular location, this branch, right? This is allowed state. Okay. So, and this is, 2 pi right here. This is a p. I'll shift it by 2 pi. Okay. Basically, if I shift it by 2 pi, this I can push it to like this. Okay. And this guy, I can shift it by 2 pi. So if I do that, I'll get another branch like this. Okay. And similarly, this one I can shift it and I can bring it to this one. And this is again shifted and going to like this. So in effect, because if you shift this, it's not going to change the energies. Okay. So we can actually represent in a simple way, in what they call as reduced K space as this. Okay. So basically you have series of bands like this. Each of them is parabolic. So this is, now if you look at around 0, right, they're all parabolic. If you go to higher case, this is parabolic near k equal to 0. Okay. So what's happening is you have this series of allowed bands and forbidden regions. Okay. And this particular diagram is called as EK relation. Okay, I promise you, this is the this is the summary of it. Even if you don't understand the entire process, it's okay right now. What I want you to take away is you can represent the allowed energies in a semiconductor using these EK relations. Okay. In the next class, I'll again talk a little bit more about EK relations, but we will use that to identify what is direct and what is indirect semiconductor. We'll do it in the next class. For now, I just want you to accept or understand that basically, if you had a free electron, it had a parabolic dispersion, right? And then if you had a confined electron, you had discrete levels, right? But the moment you get multiple atoms interacting with each other, then you get these small bands of energies which are allowed and bands which are forbidden. Okay, so you have this range of energies which are allowed, and that can be represented as an EK relation. Okay? So there are two forms of band diagrams. One is what we call as a Fourier space EK, and the other one is what I'll discuss now. In the physical space. Okay, so we refer to each, any of them. You can refer to either of them depending on the convenience. Okay, so this is a very very important picture, and I think if you understand this, you understand how the bands are forming. Okay, so this is basically a graph showing you how the distance between atoms are, right. This is basically distance between atoms. This is distance between atoms. If the distance between atoms is large, what happens to energies? Well, we are not really interested in the core electrons, 1s, 2s electrons, 2p electrons, we don't care. We are interested in the 3s because the valence shell is what I said will contribute to the electronic properties, right? So what are the valence orbitals? We have 3s and 3p, right? So we see that 3s has how many states available? It has each 3s atom has two states available. Sorry, each atom has two 3s states. And if you have n atoms, you will have two n states, right? Each of the atom has two states and you have n atoms, so two n states. And we saw that the 3s state was fully filled, right? So you have 2n electrons, which are there in those states. So basically this is completely filled. The 3s is filled. What happens to 3p? We saw that the 3p energy level is higher than 3s, right? And you had how many states? 6 states. Each atom will have 6 states because there is threefold degeneracy. And each of them can take 2 electrons. So there are two electrons states available. So 6 n states are available, but only 2 n electrons because each of those 3p has only 2 electrons. So total it has 2 n electrons. Okay, this is what happens when the atoms are far apart. Now, as you bring the atoms close, what happens? Okay, as you bring the atoms closer, as you reduce R, okay, in this case, all these states are actually degenerate, right? States, I can't, are degenerate. I'll call it degenerate states. Degenerate energy levels, right? Because all of them have the same energy because the interactions are not there. It's the atoms are very, very far apart. The interactions are not there. So there is degeneracy. But the moment you start reducing the distance between the atoms between the atoms, you saw that as you bring the potential wells closer and closer, there is a lifting of degeneracy and there is a small gap that is appearing, right? Delta E. So because of that, what happens here is as you bring the atoms closer, you'll see that this energy levels are forming a band. Okay, this is a band of energies, right? Band of, well, band of allowed energies, right? Similarly, for the 3s states, you have allowed energies. All right. So this continues, okay, when you get to the exact lattice constant, okay. This is the lattice constant, right? For silicon, it was, I think, 5.4 something, right? You just check it up, okay? 5.4 angstroms, 443 maybe, okay? So you have this lattice constant when you exactly get to that point, which is the most stable, that's when silicon lattice is stable. Okay? The energy, total energy is minimized. That's where the stable lattice forms. So when the lattice is stable, then you have basically two branches. Okay, the energy levels have interacted and they have split into two branches. One is the bottom branch, right, which we call as a valence band. Okay, okay, and the top branch, which we call as a conduction band. Okay, so that's what I have shown here. If you, I'm sorry, it's becoming a mess. Basically, this branch is basically represented here, and this branch is represented here. The energies are exact. I just took the line. Okay, so what you see is that how many states are there in this branch? Initially, there were two n states here and six n states here. So initially there were 8 n states. Okay, initially 8 n states are there, out of which 4n are filled, right? 4n electrons are there, right? That was the initial condition when R was large, right? R is large. At this point, it is like that. But as you brought the atoms closer, this band split up into 4n states in the upper. So here you have 4n states, and here you have 4n states. Okay, you have a band of energies allowed in the lower valence band, and the upper one is called conduction band. Okay, now which of them is filled up? The total number of electrons was 4n electrons. So all of them will be filled up all of them go into the 4n electrons are here. So the valence band is completely filled up, whereas the conduction band has 0 electrons. Sorry, not states, I'm sorry, 0 electrons, right? You have 4n states available, but no electrons in that. Of course, just remember, this is at T equal to 0 Kelvin, okay? I'll talk about what happens when the temperature changes tomorrow or in the next lecture, okay? So what you see is that because of this interaction, bands are forming, bands of energy levels. So if you look at these bands, right, closely, it will be like very, very, how many atoms are there in a silicon lattice? We said for every centimeter cube, there are 10 power 22 atoms. So there will be 10 power 22 levels here. Each of them is so close to each other. Okay. So it is like, the delta E will be like 10 power minus 18, 19, something like that. Okay. So it's negligible for our purposes. So we call it a band. Okay. But physically, there is still some energy, small differences, but that is insignificant. That is beyond negligible. I don't know what you can call it. Okay. So you have this valence band and conduction band. Okay. So valence band is completely filled up with electrons. Conduction band is completely empty. Okay. And separating the two is basically what we call as band gap. Okay. This is your band gap. Okay. EG. Okay. So this is where we can in principle start. I mean, you can start talking about semiconductors from here. You can say that, okay, there are this valence band and conduction band, and you can go forward from there, and you will understand the rest of the material quite well. But I wanted to give you a very strong intuitive foundation. This is probably, what is not typically done in a traditional curriculum. I have taken a very non-traditional route. I have done a little bit more detail than what I would, do it. But I think it is essential to have a strong foundation. At least you need to be aware of where the physical origin is. Okay. So I did this. Okay. So in summary, what we did in today's lecture, from all that, I want you to remember 3 things. Okay. If you remember these 3 things, you're fine for the next lecture. Okay. What are those? The first step is I want you to go and review the covalent bonding model. I said this visualization, right? 2-dimensional visualization. So go back and review what this is. Okay. This is what. It's a very useful thing. And in the next lecture, I'll start talking about, what happens, if you remove one silicon atom and put something else there. Okay. So essentially what we said was Each of these gray areas represent a silicon atom, and each of the lines represents a covalent bond. So each silicon atom is connected to 4 silicon atoms in the, it has 4 nearest neighbors, and it has 4 electrons. So because of the covalent bond, it basically shares 4 electrons with the neighbors and then forms a stable, it fills up the valence shell. Okay, because of which it forms a stable compound, right, which we can use. So this is what is the two-dimensional visualization. I want you to go back and review it if it's still unclear to you. And the second thing I want you to remember is, we had all these discretizations which are coming in, and then you have these bands forming. Finally, in silicon, you have basically, the most important thing is the valence shell. We don't have to worry about the core electrons. In the valence shell, when the electrons interact, you end up getting a valence band and a conduction band. Okay, this is a valence band and a conduction band. This is completely full. Okay, you can't add more electrons, especially at 0 Kelvin. Okay, and conduction band is completely empty. And then there is an energy gap between the two. Okay, this is the energy band representation. Okay, energy bands. This this is basically in some sense position. Okay, I didn't mention it because it's not easy to put a dot, right? But later we'll start drawing band diagrams wherein we'll draw energy bands as a function of position. Okay, that is one thing. And you can also represent energy bands in the Fourier space. Okay, energy bands in Fourier space. I'm sure this will not be that clear to you at this point of time, but unfortunately you'd have to do, if you know a little bit of Fourier transforms, you will understand that, there is an analog, if you take in a signals course, you would have seen that time and then frequency are Fourier variable. You can do Fourier transform from time to frequency and frequency to time, right? You can do that. Similarly, between space, you can do from x to k and k to x. It's a kind of Fourier transform pair. Okay, this is called as a spatial frequency. K is called as a spatial frequency sometimes. Anyway, so you can have the energy bands in the k space, and they are called as EK diagrams. Okay, these are useful for identifying what is a direct and an indirect band gap semiconductor. For that purpose, I'll use it next time. After that, we don't really use it much. Okay, except for a couple of occasions where we talk about the mobility and things like that. Okay, effective mass and things like that. We will talk. But yeah, I just want you to accept that there is a EK relation. The EK relation is essentially the dispersion. I also call it dispersion. The free electron had a parabolic dispersion, whereas if you have a bands, it takes a little bit more complicated shape because there is discretization, and each of those discrete levels are actually forming bands because of interactions, and all of that can be represented in the form that is shown in the graph on the right here. Okay, so we will again study it in a little bit detail. Okay, it's not possible. If I want to go, we have to go in a lot of depth, which is not necessary for this course at this level. But I just want you to be aware that there is this two types of band diagrams. One is as a position of x, other one is as a position of Fourier EK, basically in the Fourier space. Okay, so these three things, if you remember from today's lecture and understand them, you'll be ready to go for the next lectures. All right. With that, I would like to stop. Thank you very much for your attention. We will meet again in the next lecture. See you then. Bye.